Try this for me. Open Claude or ChatGPT or whatever you use. Give it a coding task, something non-trivial. Run it. Then clear the conversation, paste the exact same prompt, and run it again. Different result, right? Maybe the first time it wrote clean, elegant code that passed every test. The second time it went on a bizarre tangent, imported a package that doesn't exist, and confidently told you it worked. Same model, same prompt, completely different outcome. You felt this. Everyone who works with AI agents has felt this. And if you've used something like Claude Code or Cursor on a long multi-step task, you know it gets worse the longer the task runs. The agent starts strong, and then somewhere around step 12, it's wandering, doing things that don't make sense, trying to fix a bug it introduced while fixing the bug it introduced while fixing the bug. It's a mess. And a team of researchers just published the paper that puts math behind that feeling. They didn't just confirm it, they found something that changes how we should think about AI risk entirely. Because here's the thing nobody's really talking about. When AI fails on hard tasks, it doesn't fail like an evil genius. It fails like a drunk person trying to parallel park. And that distinction might be the most important one in AI safety right now. So let's back up for a second. When people worry about AI going wrong, and there are legitimate reasons to worry, the default mental image looks something like this. An AI system that's extremely capable, that has figured out what it wants, and that it pursues that goal with ruthless, superhuman consistency, even if that goal isn't what we intended. This is the classic alignment problem. The paperclip maximizer, Skynet, an AI that's coherently doing the wrong thing. But there's another way AI can fail, and it's way less cinematic. The AI could just be chaotic, unpredictable, not consistently pursuing any goal, right or wrong, just doing different things every time you ask, with errors that don't follow any pattern. Think about it like an archer. A misaligned archer always hits the same wrong spot, 3 feet to the left of the bullseye, every time. Predictable, consistent, fixable, actually. You just recalibrate. But an incoherent archer, shots landing everywhere, up, down, left, right, no pattern. That's much harder to deal with because there's nothing stable to correct. In statistics, this is called the bias-variance decomposition. Bias is systematic error, the archer always hitting left. Variance is random scatter, shots going everywhere. And the total error is roughly the sum of both. What this paper does, and it's kind of brilliant in its simplicity, is apply that framework to AI failures. They define something called incoherence, the fraction of an AI's errors that come from variance rather than bias. An incoherence of 0 means the model always makes the same mistake. It's consistently wrong. An incoherence of 1 means the model's errors are pure noise. It's a hot mess. And then they measure it across frontier models, Claude Sonnet 4, O3 Mini, O4 Mini, the QN3 family, on multiple choice science questions, agentic coding tasks, and safety evaluations. The first big result hits you right away. Across every single task and every single model they tested, the longer the model spends reasoning and taking actions, the more incoherent its failures become. Let me say that again because it's counterintuitive. You'd think more thinking would mean more consistent outputs, but it's the opposite. On questions where Claude or O3 spent thousands of tokens reasoning, the errors were dominated by variance. The model wasn't consistently getting the wrong answer, it was getting different wrong answers, every time. They show this with a really clean visualization. You sort questions by how long the model thinks about them and plot incoherence. It's basically a straight line going up. The R-squared values are above 0.9 for most models. This isn't a noisy trend, it's a clear, strong relationship. And here's what's sneaky about it. This isn't just because harder questions take longer to think about, though that's true. They controlled for that. They took individual questions and split the model's responses into 2 groups, the ones where it happened to think less than the median and the ones that it thought more. Same question, same difficulty. And the group that thought longer, substantially more incoherent. There's even a line they quote from a Claude Code user's blog post. AI agents tend to become more unpredictable the longer a conversation goes. They put that right in the paper, because that's what this is, a formal confirmation of something practitioners already feel in their bones. On swe-bench, the agentic coding benchmark where models solve real GitHub issues using tools, the pattern is even more dramatic. The more actions the agent takes, the more its behavior diverges between runs. Same issue, same model, same tools. Completely different debugging paths, completely different code. Sometimes it works, sometimes it doesn't, and the why is basically random. Now, you might think, okay, but if we just make models bigger, smarter, more capable, surely that fixes the incoherence problem. Bigger models are better at everything, right? Not here. This is the second big result, and it's the one that I find genuinely surprising. They tested the QN3 family models, 1.7 billion parameters up to 32 billion on MMLU grouped by question difficulty, and the scaling behavior splits in a really interesting way. On easy questions, the ones that smaller models already get right most of the time, bigger models do become more coherent. They not only get the answer right more often, they get it right more consistently. Great, that's what you'd expect. But on hard questions, the frontier of what these models can do, bigger models become more incoherent. They get the answer right more often overall, sure, their accuracy goes up. But when they're wrong in increasingly random ways. The variance doesn't shrink as fast as the bias does. And this is where the paper gets really precise. They compute actual scaling laws for bias and variance separately. And what they find is that bias scales down at roughly the same rate regardless of question difficulty. But variance, on easy questions, it drops fast, faster than bias. On hard questions, it barely drops at all. So as you make models bigger for the hardest questions, variance becomes the dominant source of error. Which means on the problems that actually matter, the hard frontier difficulty tasks where we most need AI to be reliable, making models bigger makes them less predictable when they fail. They also did something clever that I want to talk about. They ran a survey. Well, actually, they reused a previous survey by one of the authors, where they asked separate groups of people to rank entities by intelligence and separately by incoherence. Entities like AI models, animals, famous humans, organizations, and the correlation is striking. Across almost all categories, things that people judged as more intelligent were also independently judged as more incoherent. There's a Spearman correlation of 0.89 for AI models, 0.95 for non-human beings. The one exception is individual humans, where the correlation is slightly negative. We find the smartest humans slightly more coherent. But for organizations, animals, AI systems, intelligence and incoherence go hand in hand in our perception. It's almost poetic. The smarter the entity, the harder it is to predict where it'll mess up. Now, here's where this gets practical and a bit uncomfortable. If you take these results seriously, they shift the center of gravity for how we should think about AI risk. The classic worry is, what if AI becomes coherently misaligned? What if it's a ruthlessly consistent optimizer pursuing the wrong objective? That's the Bostrom scenario, the Nick Bostrom superintelligence paperclip maximizer. And this paper doesn't say that can't happen. It doesn't rule it out. But it provides empirical evidence that at least with current architectures, the default failure mode is the opposite. As AI gets more capable and tackles harder tasks, it gets messier, not more focused. The failure mode looks less like a calculated betrayal and more like an industrial accident. The paper actually has a beautiful way of putting it. They note that LLMs are dynamical systems, tracing trajectories through a high-dimensional state space. And the set of dynamical systems that act as consistent optimizers of any fixed objective is, mathematically, measure zero in the space of all possible dynamical systems. Meaning, being a coherent optimizer is the exception, not the rule. We shouldn't expect AI to naturally converge on consistent goal pursuit any more than we'd expect a random equation to describe a straight line. And the second part, variance accumulates over trajectories unless there's an active correction mechanism. Every step an AI agent takes in the real world, every tool call, every code edit, every decision is a place where noise can enter. And in the real world, unlike in a benchmark, you often can't rewind. The state has changed, the email was sent, the code was deployed, the variance compounds. But there's a nuance here that keeps this from being all doom. They found that some things do reduce incoherence. Ensembling, running the model multiple times and aggregating the answers, reduces variance at a rate of 1 over the ensemble size, exactly as theory predicts. Double the samples, half the variance. That's clean and actionable. And increasing the reasoning budget, telling the model think harder, does slightly reduce incoherence for most models, though interestingly that effect is much smaller than the natural variation. The difference between a model that happens to think long versus short on the same question is way bigger than the difference between telling it to think a little versus a lot. So there are engineering paths forward. Error correction, redundancy, majority voting, these are proven strategies for dealing with variance. They just look very different from the strategies you'd use against coherent misalignment. If your AI is a focused adversary, you need better alignment techniques, value learning, interpretability, oversight. But if your AI is a hot mess, you need better engineering practices, redundancy, validation, rollback mechanisms, ensemble methods, the same toolkit we use for any unreliable system. And the paper is honest about what it doesn't tell us. This is about current architectures, current training methods, current frontier models. A fundamentally different architecture could change the picture. And they note that in settings with poorly specified training objectives, which is basically all real-world deployment, there's another component of bias called specification bias that their benchmarks don't capture very well. The model might learn to optimize a reward signal perfectly, but the reward signal might not capture what we actually want. That's the reward hacking problem, and this paper actually increases its relative importance. Which brings us to something that I find genuinely interesting to sit with. The researchers essentially trained small transformers to literally be optimizers. They gave them training data that was, here's the state, here's what a hand-coded optimizer would do next, and watched what happened as they scaled these models up. The models got better at optimizing. The overall loss went down. But the key question was, does the model learn what to optimize faster than it learns how to optimize consistently? And the answer is yes. The bias, the gap between the model's average behavior and the correct optimization trajectory, drops much faster than the variance. The scaling exponent for bias was 2.165. For variance, it was 0.877, meaning models learn the right objective relatively quickly, but they remain noisy in how they pursue it. And as you make them bigger, the gap widens. The model knows where to go, but can't walk a straight line to get there. That's the hot mess in miniature, and it's not a bug in these specific models. It seems to be a structural feature of how language models scale. If you're someone building with AI agents right now, this should change how you think about reliability. The failure mode you should be designing for isn't the agent decided to do something adversarial, it's the agent did something random and weird on step 15 of a 20-step task, and now everything downstream is wrong. That's the engineering challenge. And it's one we actually know how to approach. We've been dealing with unreliable components in engineering for centuries. But if you're someone thinking about long-term AI risk, this paper is more like a data point than a conclusion. It says with these models, these training methods on these tasks, the dominant failure mode is incoherence. Whether that holds as architectures change, as training methods evolve, as models encounter situations that create strong selection pressure for coherent goal pursuit, that's still an open question. The paper doesn't close it, but it does tell you where the empirical needle is pointing right now. And right now, it's pointing at a future that's less Terminator and more, that coworker who's really smart, but every time you give them a complex project, you have no idea what you're going to get back. That, at scale, with real consequences. Which honestly might be harder to solve than a villain, because at least a villain has a plan you can study. This paper does something I think the AI safety field needs more of. It replaces vibes with measurement. Everyone has intuitions about how AI fails. This team built a framework to actually quantify it. And the framework is general enough that as models evolve, you can keep measuring. You can track whether incoherence is going up or down. You can compare architectures, training methods, deployment strategies. That's how science is supposed to work. Less AI might be dangerous because I can imagine a scary scenario, and more, here's exactly how AI fails, here's how that scales, and here's what it implies for which risks to prioritize. If you're working with AI agents and want to understand why your results are inconsistent, now you have a framework. And if you're thinking about AI safety and want to know what kind of failure to actually prepare for, now you have data.